Okay, let's make a start. Welcome everyone. My name is Daniel and I'm your Year 9 teacher. We are going to begin the Year 9 class for today at Mathspace Academy. If you've just got here, welcome, sit back and let the learning begin. So this is lesson 2. We started Mathspace Academy last week. That was the first lesson. So if you're joining me for the first time today, welcome. This is now the second lesson. And so we're going to be continuing our work on the real numbers, and this is a Year 9 class. So, what is a light year? That's where I'm going to start today. So a light year, you might have heard this in, science fiction, movies, television, books. A light year is actually a distance of length. So you might think it's time because you see the word year, but it's actually a really large length in meters. So when you think of, neighboring galaxies in our universe, they could be thousands of light years away. And so a light year is formally defined as that distance that a beam of light would travel in 1 year. So I can see this is 9460730, and then I have all of these zeros coming afterwards. So a 6-digit number, remember, is a million. A 9-digit number is a billion. A 12-digit number is a trillion. So we're actually looking at 9,460 trillion meters. That is the distance of 1 light year. So that's a really large number. And the problem is it's too large. So you type this into a calculator and you're going to get a funny number that appears, because calculators are really only designed to work with 10-digit numbers. Now, the mass of 1 uranium atom. Now, uranium, when you know your chemistry and physics, it's actually a heavier atom compared to the other atoms in the periodic table, but we're still talking about 1 atom. So that's really, really tiny. So if we look here, I think there's something like 18 zeros. Let me count. So it's 0.369121518, 21 zeros after the decimal point, then 395 of a gram. So that is really, really tiny. You try put that into a calculator and it's just going to round it down to 0 unless you use something called scientific notation. And so that is what we're going to be learning about today. How do we operate with numbers that are really large and really small? This is why we use scientific notation. So that's the introduction to my lesson for today. We're going to be talking today about scientific notation, what it is, how it's used, how to convert between standard numbers and numbers in scientific notation, and what we'll look at a lot as well as applications. So what is this used for in real life? So who am I? My name's Daniel O'Kane. I am a mathematics educator and teacher I work at Mathspace. You might have seen this face before if you've looked through the online textbook a lot in the Mathspace app, because I've created thousands of worked example videos that appear in those textbooks. I used to be a lecturer at Swinburne University before I started working at Mathspace, and I have over 10 years experience teaching both online with students and also directly in the classroom. Just some housekeeping before we jump into the lesson. So I mentioned this last week, but I'll just say it again in case you're new. We can't cover everything in 1 hour in a week. So if you were learning scientific notation in school, you would probably spend 1 to 2 weeks just covering scientific notation. And so you would go into more depth and you would really practice that skill. So today, this is just a 1 hour recap of everything in scientific notation. So if you've learned scientific notation at school already, great. This is going to be a good recap for you to hopefully really solidify your learning. If you haven't covered scientific notation yet in school, that's okay. I recommend sticking around and watching anyway, start to get your head around these concepts so that when you do see this work in school, you'll then be more prepared. So I follow the Mathspace curriculum, and so we have these online textbooks, and so I'm using that curriculum to teach week by week, but it's okay if you're not using Mathspace. This is welcome for everyone. Everyone in Australia can come along and come to these classes. So if you don't have Mathspace, don't worry about it. But if it is something that you would like to try or look at, if you're a student, I recommend talking to your teacher. If you're a teacher, I recommend getting in contact with us. So today's class will be recorded. So if you have to leave early, for example, you're here with me now, you will be able to watch the recording at a later date. And so that's going to be available at the website. I believe I've actually put that link in wrong. It should be mathspace.co/au/academy. Now, you can use the chat today if you wish to talk to one another. You can say hi and whatnot, but I would ask please for you to use the chat sensibly. Okay, if you're not using the chat sensibly, I will give you a warning. And if you still misbehave, I might have to kick you out of class. And I don't want to do that, but hopefully let's just use the chat respectively. So feel free to say hi to one another. And if you want to talk to each other specifically about the content, I wouldn't just, chat away. You want to be engaging with what I'm teaching you today. There is a Q&A button in Zoom that you will have noticed. And if you click that, that's where you can ask me questions. So if there's anything you want me to clarify, if you've got a question from something you're working on at school, there'll be time at the end of today's class for me to answer some of these questions. So I'll make sure that I leave 10 minutes at the end. We will finish at around 11 o'clock. These classes just go for the hour. But what I have to get through today will probably take 45, 50 minutes. And then at the end, we'll have time for questions if you like. And so, yeah, if you want to ask me questions, just drop them in the Q&A box and I can tackle them later. So what are we doing today? So this week, we're continuing our work on real numbers. So if you were with me last week, we did indices and we looked at index laws. And so we're going to apply some of those index laws now when we talk about scientific notation. And that's what we'll be doing today. So it's actually lessons 3 and 4 from chapter 1 of the Mathspace Australian Year 9 curriculum. And next week, we're going to start our work on algebra. So I'll start working with variables, just a basic introduction to algebra, and then how indices can apply to that. And then we'll also start working with the distributive law. So that's expanding brackets and factorizing. So that's for next week. If you want to do some more learning on the topics that we've covered this week and last week as well, there's this maths teacher, his name is Eddie Wu. He's a famous Australian maths teacher. You might have heard of him. And so he's got all these great online videos that you can use to help you learn. And so it's videos of him in the classroom. And so he's recorded them and he's a very engaging teacher. Now, if you come to wootube.mathspace.co, you can actually then look up the Australian curriculum and you can actually go to the real numbers, chapter 1. And this is just exactly how you see it mapped to the Mathspace curriculum if you're using Mathspace. So you can see there are 4 videos he has on introducing scientific notation and then another 4 videos on using scientific notation. So if you want, after this lesson or another time, you can go review those lessons and you're going to get a deeper dive into what we cover today because I've only got an hour with you. He's got more time with you. I'm just putting this up as my first 2 slides, the multiplication law of indices and the division law of indices. So remember, when you have the same base and you multiply each with different powers, it's the same as just adding those powers together. And the division law is the opposite. When you divide 2 numbers where you're working with the same base, but then you have these different indices, you just find the difference between these numbers. So I'm going to use these 2 laws and the negative index law when I talk about scientific notation throughout today's class. So here it is, scientific notation. So you have a number times 10 to the power of n. So A, this number, it's any number between 1 and 10. You can include number 1, but you cannot include 10. This does include 9.99999, but it doesn't include 10 for that value of A. So you can have a unit but it doesn't have to be a whole number. It can be any rational number, or it can be a rounded irrational number. So it has to be a rational number, this value of a between 1 and 10. And then n, this power of 10, sorry, that can be any integer. So it's got to be a whole number, but it can be positive and it can also be negative, and it can include 0 as well. So that's the formal definition of scientific notation and what it is. So, who came up with scientific notation? Where did this come from? So historians have observed that Archimedes of Syracuse actually was someone who started using a form of scientific notation. Not scientific notation precisely, but he was working with this concept of really large and really small numbers. So Archimedes is a very famous Greek mathematician, astronomer, physicist, engineer, and inventor. He's credited with a lot of different mathematics discoveries, especially the work in circles, okay? And there was a man named King Galo who asked a question to Archimedes. How many grains of sand do you think could fit in the whole universe? And so Archimedes had to think about it. And so he had to think about, how much sand is there on the planet Earth? And so he came up with this answer of 8 vigitillion. So you and I, we know million, billion, trillion, but once it gets larger than that, it's not really well known. There are lots of different names for as you go larger than a trillion. And a vigitillion is a number with 63 zeros afterwards. So 8 vigitillion, you can write in scientific notation as 8 times 10 to the power of 63. So we're going to talk more about scientific notation soon. And, how do I know that it's 63 zeros after the 8? Well, that's how I read the scientific notation. So do keep in mind, back in the times of BC, the universe as they knew it was much smaller as the universe as we know it. So actually for us as astronomers now in today's world, we know that the universe is infinitely expanding. So if it's infinitely expanding, this is actually technically a question that could never be answered. But even though Archimedes was wrong, he gave it a good go based on what he knew back then. And 8 times 10 to the 63, that is a very, 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 very large number. You're talking about millions and millions and millions and millions of trillions and larger than that. So, okay. So last week when we were talking about index laws, we talked about the 0 power law. So any base to the power of 0 is 1. We can actually think of all of the numbers in our number system as multiples of powers of 10. You might know our number system is a base 10 system. So you look at ones, tens, hundreds, thousands, tens of thousands. So, you multiply by 10 as you add digits going from right to left. So 10 is 10 to the power of 1. 100 is 10 to the power of 2, 10 times 10. 1,000 is 10 to the power of 3. So it keeps growing larger and larger and larger, the larger the number you're looking at. If I take a basic number like 300, you might remember this place value table. You probably would have seen it in kind of late primary school, early high school. So 300 can be written as 300s, 0 tens, and 0 units. So if 100 is 10 to the power of 2, a 10 is 10 to the power of 1, and a unit is 10 to the power of 0, I can actually write 300 as 3 hundreds. And then I don't need to worry about the tens and the units in this case because there are none to consider. And 100 is 10 to the power of 2. So what I've just shown you is that 300 can be calculated to be 3 times 10 to the power of 2. So 300 is your standard number, how we normally recognize numbers. And then 3 times 10 to the power of 2 is that same number, but now expressed in scientific notation. We can do the same thing with decimal places. So 0.1, that's 1/10, remember. You're looking at tenths in that first digit after the decimal point. So 1/10 is 10 to the power of -1. 0.01 is 1/100th. So I can write 1/100th as 1 over 10 to the power of 2. And using negative indices, that negative index law, I could express this as just 10 to the power of -2. So you can keep doing that as you move from left to right away from that decimal point. So 1,000th is 1 over 10 to the power of 3. That's going to be 10 to the power of -3. And so this just keeps going. So now you're starting to hopefully think about how these really large numbers and really small numbers, like I talked about at the start of the presentation, they can actually be expressed much easier if we were to convert them to scientific notation, which we'll look at later. So looking now as an example, 0.009, okay? 0.009, if I use that place value table that you remember from early high school, late primary school, that's 0 units, 0 tenths, 0 hundredths. There's just the 9 thousandths. So I could now write this as the units as 10 to the power of 0, the tenths as 10 to the power of -1, the hundredths as 10 to the power of -2, and the thousandths as 10 to the power of -3. So then 0.009 is just 9 lots of 10 to the power of -3. So I can write 0.009 because it's an easier number to convert. That's 9 thousandths. So 9 thousandths is 9 over 10 to the power of +3, which is going to be 9 times 10 to the power of -3. Okay, so I'm going to stop the presentation for a moment, and I'm actually going to now answer some questions in Mathspace. Okay, great. So which of the following numbers shown here is written in scientific notation? And so we have these 3 choices. Okay, we have 709.92 times 10 to the power of 18. We have 9.92 times 10 to the power of 18. And we have 0.299 times 10 to the power of 6. So I know that the first and the third answer is incorrect. Why is that? Because both of these numbers are not between 1 and 10. 0.299 is less than 1. 709.92 is greater than 10. So that only leaves me with this option. So the 2 checks on whether a number is correctly in scientific notation is to see that that number at the front, so 9.92, I need that to be between 1 and 10, okay? And then that power of 10 needs to be an integer. So 18 is an integer, so that means that yes, 9.92 times 10 to the power of 18 is the only number here written in scientific notation. Okay, going to the next problem. The thickness of coating on a camera lens is 0.000001 meters. Express the thickness in scientific notation. So looking at 0.000001, I can see this decimal place. I could jump backwards 1, 2, 3, 4, 5, 6 times from the end of the number to that 0 at the end there. That's 6 jumps in order to go from where the decimal place is now to where it's supposed to be, okay? Now keep in mind, remember that third digit was 1,000ths, so that's 10 to the -3. The fourth digit would be how many tens thousandths. The fifth digit would be the number of 100,000ths, so 1 over 100,000. And then the sixth digit, so that is millions, the number of millions, with the TH at the end. It's a bit hard to say. So I can actually write this as 1/1,000,000 as the thickness of this camera lens coating, okay? And so 1,000,000 I can write as 10 to the power of 6. And as I've shown you in my work, okay, that is the same as using negative index laws, 10 to the power of -6. So you can have this as your answer, 10 to the power of -6, and that is correct, okay? Also, what would be correct if you're writing specifically in scientific notation is you can write 1 times 10 to the power of -6. So that is also a correct answer when we're expressing this thickness in scientific notation, but you have to remember the unit of measurement as well. So often in Mathspace, we give that, there's a meters already there, but if you were writing this answer in your books and presenting this to your teacher, you'd have to remember to write the unit of measurement, which is in this case, meters. Okay. So I'm now going to quit this. I don't think I had another question for us yet. No, that's for later. Okay, so I'll jump back to the presentation. Ooh, wrong button. Pardon me. Present. There we go. I did this one already. Next one. Okay, a little trickier example now, 5,215. So I now know the thousands are 10 to the power of 3, the hundreds, 10 to the power of 2, et cetera, et cetera. So I can now write 5,215 as the addition of these 4 numbers in scientific notation. So 5 lots of 10 to the power of 3, 2 lots of 10 to the power of 2, 1 lot of 10 to the power of 1, and 5 lots of 10 to the power of 0. So in order to add these 4 numbers together now in scientific notation, what I'm about to show you is just an explanation of why scientific notation works and some of the reasoning behind it. You wouldn't be required to do this level of calculation to convert a standard number to a scientific notation. I'm going to show you a really quick and easy way of how to do this in a moment when you're looking at several digits. So I'm going to take these 3 numbers now, and I'm actually going to convert them to be in terms of 10 to the power of 3. So they won't technically on their own be scientific notation anymore, but this is how I'm going to be able to add these 4 numbers together. I want them all to have that same power of 10. So 2 times 10 to the power of 2, if I want to write that with a 10 to the power of 3 now, let me just get my annotation. So if I want to write that number 2, so this number 2 I can write as 0.2 times 10. And the reason why I'm doing that is because now I can group this together, 10 times 10 to the power of 2, and that becomes 10 to the power of 3. Now looking at this next number, 1 times 10 to the power of 1, if I annotate on this, so 1 I can write as 0.01 times 100. And the reason why I'm doing that is I now want to multiply 10, which is 10 to the power of 2, by 10 to the power of 1. And multiplication law that I showed you before is going to create 10 to the power of 3. So what I'm doing is I'm taking those 3 numbers that I circled in red before, and I'm expressing them all as a multiple of 10 to the power of 3. That way, I'm going to be able to add all of these numbers together in a moment. So that's what I'm doing. So just if you're not quite sure what I'm doing yet, just keep following along and I'll show you, okay? So the 5 I can write that as 0.005 times 1000. And the reason is I can multiply 10 to the power of 0. Well, that's just 1 anyway, so I don't really have to worry about it. So then I can write this now as 0.005 times 10 to the power of 3. So now all of these numbers I have in terms of 10 to the power of 3. So I'll just circle those numbers because I'm about to carry them over to the next part. 0.2 times 10 to the power of 3, 0.01 times 10 to the power of 3, and 0.005 times 10 to the power of 3. So now when I look at 5,215, I can add 5, 0.2, 0.01, and 0.005 together because they've all been multiplied separately by 10 to the power of 3. So I'm just taking out that 10 to the power of 3 as a common factor. So then I can write this now as 5.215 times 10 to the power of 3. So that's just showing you how this works, this scientific notation, and why this base 10 system is able to help me do these calculations. But now I'm going to show you the much easier way of how to convert numbers between scientific notation and standard form. Okay, so if I'm going to convert a number in scientific notation to a standard number, it's very easy. When n is a positive integer, you just want the decimal place to jump forward by how many digits that is given in that number n. So if it's 10 to the power of 3, for example, the decimal place is going to jump forward 3 times. And when n is negative, that decimal place is going to jump backwards by that many digits. So if it was 10 to the power of negative 2, for example, that decimal point is going to jump backwards twice. So if I look at this example now, I'll just annotate again. So 5.234 times 10 to the power of 8. What I'm doing is with this decimal, I'm jumping it forward 5, 6, 7, 8 times. And then when it jumps past its numbers, you replace these numbers with 0. Okay, so if there's nothing there and the decimal point is still jumping forward, you just add these zeros. So now this is my answer. So 5.234 times 10 to the power of 8, that is 523,400,000. I see a lot of action in the chat box. I'm just having a quick look to see how it's going. Okay. It's just some random chat. No one's being too rude yet. So, yeah, look, I don't think this is really productive. I'm going to turn off the chat. All right. Okay, let's keep going. So, let's keep going. Now looking at this number, 6.111 times 10 to the negative 5. How do we convert this number in scientific notation to a standard number? So the decimal point was here. And according to that rule I mentioned before, if it's negative, you want to then jump that decimal point backwards 5 times. 1, 2, 3, 4, 5. So then the decimal point is going to exist here now. And because this is a number less than 1, I can write 0 out the front. So then 0 point, I've got these 4 zeros and then the remaining digits, 6111. So I've converted 6.111 times 10 to the power of negative 5 to be 0.00006111. So that's an easier way versus that place value table work that I was doing before to convert a number in scientific notation back to a standard number. So now we can look back at those numbers that I was talking about at the start of the class, okay? I need to clear those now. So now that light year, remember, that was 9460, 730, and a whole bunch of zeros afterwards. I can see the decimal point would need to jump 15 digits forward in order to be able to create this number. So I'll show you how I do that. So if I had my digit here, okay, and it has to be there, remember, because that number in the front, okay, has to be a number between 0 and 10. So if I go 9 point, and now I jump this forward, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I've made 15 jumps forward to create this number. So then I can write the remaining digits, 4, 6, 0, 7, 3, but then there's no reason for me to write the rest of these zeros. I don't have to worry about them. So 9.46073 times 10 to the power of 15 meters. Okay, so that decimal point after the 9 had to jump forward 15 times to create this number. So then that's how you can write this measurement, this light year, in scientific notation. And so I can see that's the correct answer. Now I can look at the mass of that one uranium atom that I was talking about in the start of the class. So this decimal point would actually need to jump backwards 22 times in order to create, if this was in scientific notation, it would have to go backwards 22 times to create this number. So let's do that again. My decimal point would have to be here at 3.95 so that I have a number between 1 and 10. And then, so how many times does this have to jump backwards? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So 22 times, that's how I got this. So then this mass in scientific notation, I can write now as 3.95 times 10 to the power of negative 22 grams. So this number that previously had all of these digits that I wasn't able to fit into a calculator, now I can if I use scientific notation. Okay, I think that's everything in the slides for today. And there's my answer. Great, so now we're going to spend the rest of the class doing some applications of scientific notation. So it won't be so much of the skills drilling. I'll do a little bit of that, but mostly it'll be see how scientists and engineers, what kind of problems are they answering when they really do need scientific notation, or when scientific notation becomes very useful. I better double check the time. Okay, yeah, we've still got a good 10-15 minutes, great. So now I can start to use some of the index laws from last week to simplify, and then I can use scientific notation to get the answer. So using index laws to simplify this, how I would tackle the question, you could do this another way, but I'm going to group the numbers together, 3 times 8, and then I'm going to have 10 to the power of negative 2 and 10 to the power of 9. So then 3 times 8 is 24. So I can just write that as 24. And now I'm going to use index laws to simplify 10 to the power of negative 2 times 10 to the power of 9. So remember from last week, you're adding the powers. So this is 10 to the power of negative 2 plus 9. So that's going to be 10 to the power of 7. So I've got this answer of 24 times 10 to the power of 7. But take a look at that. Mathspace hasn't accepted this as the final answer. Why is that? It's because 24 is not a number between 1 and 10. So I have to look now at 24 as a number. Okay, well, that's the same as 2.4 times 10. So I could write this now as 2.4 times 10 times 10 to the power of 7. Well, if I multiply 10 to the power of 7 by 10, I'm going to get 10 to the power of 8. I'm adding 1 to the power. So then that becomes my answer in scientific notation. I can use division law as well to help me simplify. So index laws to simplify the following: 7 over 35. So I'm actually already starting to read this as using fractions 7 over 35 times 10 to the power of -1 over 10 to the power of -4. So you're allowed to do that when the only operations in the numerator and denominator are multiplication, okay? So I'm taking an algebra simplification. So two numbers multiplied in the numerator divided by two numbers multiplied in the denominator, I can write as two fractions being multiplied together like this. That's how I've managed to go from here down below to here, okay? So I get 7 over 35 times 10 to the power of -1 over 10 to the power of -4. Now you could use negative index laws to write these two negative indices as positive powers. I'm not going to do that. I'm going to take the 7 over 35 and I'm going to write that as 1/5. I've simplified that fraction, divided the top and bottom by 7. And then 10 to the power of -1 divided by 10 to the power of -4, well, I can use that that division law. It's usually the second law taught in index laws, okay, to simplify this to become 10 to the power of -1 minus -4. So watch the negatives, be careful. So if I'm subtracting -4, it's the same as adding the 4, okay? And so adding the 4 to -1 would give me 3. Again, my work is not yet finished. Why? Because 1/5 is not a number between 1 and 10. So 1/5, as a decimal, I can write that as 0.2. So that is the same as 2 over 10. So in scientific notation, I can write that as 2 times 10 to the power of -1. So 1/5, if I write that now in scientific notation, 2 times 10 to the power of -1, now I can use that multiplication law for indices to add the powers here. So I get 2 times 10 to the power of -1 plus 3. And so that's going to give me 2 times 10 to the power of 2. If I was to write that as a standard number, that would just be 200. But that's not what I was asked to do. I was asked to give the answer in scientific notation. So you can use scientific notation now to start operating with numbers of different magnitudes. So if you think about it, looking at this problem, 7 times 10 to the power of -1, this number in the numerator, that's 7/10. And then 35 by 10 to the power of -4, well, that was 35 over 10,000. Okay. So that's 0.00, I believe it's 35. Yeah. So what I did was I just took 0.7 and divided it by 0.0035. Well, that would have been quite tricky for me to do without the use of a calculator. So scientific notation actually made this easier for me to do. Okay, let's jump to the next tab. I better check the time. We've got a lot of questions still. That's right, I can keep working for another 5 minutes. So you could start to use scientific notation now to answer questions like this. I'm not going to finish this question. I'm just going to start it because I do want to work on some of the other questions that I've got, which are more application-based questions. They're questions to do with space and cool stuff like that. Okay. So you can start working with these numbers of differing magnitude and then use scientific notation to make the calculation easier. So 30,000, starting with that. Okay, I know it's 3 times 10 to the power of 4. Okay, this decimal point at 3 needs to jump forward 4 times. Okay, 0.005. I know is 5 times 10 to the power of -3. Because that decimal point from 5 needs to jump backwards 3 times to create this number. Okay, 0.00002. I can write that now as 2 times 10 to the power of -5. So as you get practice with scientific notation, this will become easier. So that 2's jumping back, that decimal point, 1, 2, 3, 4, 5 times, 5 jumps. And then finally, I have, what's this? 1,100,000,000. So I'm gonna write all these zeros in here. Okay, I can write this as 1.1 because that's where the decimal would have to start to be a number between 1 and 10. And then this decimal jumps 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So then 1.1 times 10 to the power of 9. So now when doing this multiplication, I could just multiply the 3, the 5, the 2, and the 1.1 together, and then multiply each of the 10s. 10 to the power of 4 times 10 to the power of -3 times 10 to the power of -5 times 10 to the power of 9. And note, I'm not writing that 10 times 10 times 10 times 10 with the different powers. I'm just using the multiplication law to now just add those powers together. So 4 minus 3 minus 5 plus 9. So 4 minus 3 is 1. 1 minus 5 is -4. -4 plus 9 is 5. So then to solve this, all I would have to do is multiply 3 by 5, which is 15, by 2 is 30. So let me clear this, okay? So I've got 30 times 1.1, so that is just going to be 33 times 10 to the power of 5. But then if I'm going to answer this in scientific notation, I need to take the decimal point back 1, okay? Which means I have to then add another 1 to the power. So 3.3 times 10 to the power of 6 becomes the answer to this question. So I did rush through this question a little bit because I want to get to the next question, because this question, no, I'll do the other one, the next one. So a nanometer is being defined as a billionth of a meter. So another great application of scientific notation is actually converting between units of measurement, okay? So a nanometer, 1 billionth of a meter. So we can write 1 nanometer is 0.000000001 meter, okay? So the diameter of a helium atom, so again, we're talking about this atom, very, very tiny, it's a particle, okay? Can't even see it using a microscope, all right? You have an approximate size of 0.1 nanometers. So then how many atoms would fit then in a 3 centimeter sample? So we're just assuming that we're kind of lining them up in a row to create 3 centimeters, okay? So 0.1 nanometers, okay? I can write this number, 1 nanometer, as 1 by 10 to the power of -9, okay? And you can also write that as just 10 to the power of -9 meters. That is the size of 1 nanometer in meters, So 0.1 nanometers is going to be 0.1 times 10 to the power of -9 meters, okay? Just replacing that unit of measurement, nanometer, with 10 to the power of -9 meters. So then 1.1 is 1/10, right? So that's 1 times 10 to the power of -1. So if we're going to write 0.1 nanometers in meters, okay, you need to add these powers together using the multiplication law for indices, and you'll get this in scientific notation to be 1 times 10 to the power of -10 meters. Okay, so how many helium atoms is going to fit in a 3 centimeter sample, assuming that we're looking at a line just of 3 centimeters? How many helium atoms could sit next to each other? Well, how we can work this out is we can take the 3 centimeters, which, by the way, remember, is 3/100ths of a meter. So you can write that in scientific notation as 3 by 10 to the power of -2 meters. All right. So you take that length of the sample, 3 times 10 to the power of -2, and then we want to divide this into lengths of 0.1 nanometer. So remember, that was 1 times 10 to the power of -10. So this is how many helium atoms are going to fit in this sample. And so there is no unit of measurement because we're looking at a number of atoms, okay? So actually, when you look at 3 times 10 to the power of -2 meters divided by 1 times 10 to the power of -10 meters, okay, the meters measurement actually cancels out. So we're looking at a number of atoms, okay? So then, just like before, I can do 3 divided by 1. That's just 3, okay? And then 10 to the power of -2 by 10 to the power, divided by 10 to the power of -10 is going to be 10 to the power of -2 minus -10, okay? So remember, subtracting a negative number is the same as adding that number. So we're going to get as our answer 3 times 10 to the power of -2 plus 10. So I get an answer of 3 to the power of 8. Okay, so what's 3 by 10 to the power of 8? Okay, as a number, this is optional for the question, you don't have to do this, but 3 times 10 to the power of 8 would be 3 and then 8 zeros afterwards. Now, you probably don't really use these commas anymore, but I just want to use them to illustrate what this number actually is. It's 300 million. So then 300 million atoms of helium is going to fit in just a 3 centimeter sample. And so that's how you can use, have I done that wrong? 1, 2, 3, 4, 5, 6, 7, 8 million. Oh, no, I'm right. Yeah, okay. So, yeah, 300 million of these atoms, okay? All right, I think we're at near the end of the class now. So what I'm gonna do is I'll stop sharing my screen, and now I'm gonna look at the Q&A. Okay, and all these questions are pretty basic. Ben, how's your day? Someone has asked me, how is my day? I'm going to say, I'm having a great day. It's good. It's a little warm in my office, but otherwise good. Okay. Someone's asked me, what's 9 plus 10? 19. And that's it there. Okay, let's dismiss these questions. Great. Okay, so we've still got a couple minutes left of today's session. So if you have any questions for me, now would be a great time to write them in the Q&A box, okay? And then I can answer them. And I can actually share my whiteboard. So what I can do in this platform is I can actually share a whiteboard screen and I can answer a question on the whiteboard if you've got one for me, okay? So if you've got anything that you're working on at school at the moment, especially around indices and scientific notations, you can ask away. So I'll give everyone just 1 or 2 minutes. Otherwise, we can finish early. That's an option as well. But yeah, some of you might now be leaving because you don't have any questions. If you're taking off, thank you very much for coming. I appreciate you being here, and hopefully you've gotten something out of today's class where now you've got a greater understanding of scientific notation, and more importantly, why we bother with it. Okay, why are you learning this in class? That's the favorite question students like to ask their teachers in class. You know, why do I have to do this? Well, hopefully you've gotten something out of it today. So definitely if you want to pursue a STEM career where there's a lot of demand and a lot of money, okay, if you're looking to be an engineer in the future, or perhaps a mathematician, or, you know, even if you're working in data analysis, a lot of different career options there. Got to be able to used to working with very large and very small samples of data. So being able to express these numbers is very important. What I should mention is that in your calculators, you might be used to seeing this. So I know I used to do this sometimes. I used to write as many 9s as I could in my calculator and then multiply it by as many 9s as I could in my calculator to try and understand what a really big number would look like in the calculator. And so I would usually get something along the lines of 1E, you know, 20. And I would look at that and I'd be like, what does that mean? I don't understand what this is. That's actually scientific notation, okay? So it reads as 1 times 10 to the power of 20. So you can read that E in a scientific calculator as times 10 to the power of, and then this number is that power of the 10, okay? So you can now start to use scientific calculators as well to help you answer questions in scientific notation. Okay. Great. Just looking at some of the Q&As, people asking some questions. Someone's asked how many weeks do we have of this? So we're planning to run these lessons every week on Thursdays at 10 a.m. all the way till the end of term. And of course, depending on the world and Australia and the coronavirus, if we were going to be doing online teaching again as a country or as a state in term 3, we would definitely keep these going. Okay, and it also depends on demand as well. You know, if I get to the end of term and there's only 2 people coming to my class, probably not going to bother running them again in term 3. But if I keep up the attendance, if there's lots of people coming to the classes and there's lots of demand for this kind of work, yeah, we'll keep going for the rest of the year. It just really depends on, you know, the current climate and, you know, like teachers, whether they'll be still teaching online in future terms or not. So yeah, I'm just answering this question live of how many weeks do we have of this. Definitely for the rest of term 2, I'm going to be teaching these classes once a week. And so next week I'll be doing algebra, and then in future weeks, you know, I'll be looking at trigonometry and Pythagoras' theorem, etc. Okay. Someone asked if we could please go back to that last question. That might be the nanometer question. Happy to do that. So I'll stop the share of the whiteboard and I'll share my screen again. Hopefully they're still here, the person who asked that question. Yes. Nivara, yes, you're here still. So yeah, this was the question that I had on the screen before about the nanometer being a billionth of a meter. So you're more than welcome to read that question and write it down if you wish. Also remember, we're recording this session. So the recording of the session will be available in 1 or 2 days' time, and you'll be able to come back, look at the recording, and then you can stop and start anywhere in that recording. So if I did rush over something that you didn't kind of get a chance to write down, you can go back and look at the video, and that should be able to help you out there. Okay. All right, team. Now, if you're working in Mathspace, you can go ahead and now do 2 more tasks. And you can actually finish all of chapter 1, the real numbers. So if you're in year 9, working in the Australian curriculum, or you could be in a different, like Victorian curriculum, it's got the same lessons in chapter 1. Okay, those 4 tasks on indices and also scientific notation, you can actually now complete them in Mathspace if you're using Mathspace at your school. And then so that way you can keep practicing the work that we did today and also the work we did last week. All right, I'm going to finish up there. Thanks very much for coming, everyone. And I'll see you same time next week, 10 a.m. And we're going to start work on algebra. Okay? Cheers. Bye-bye.